Hi, welcome to my video where today we're going to be talking about absolute value functions. We're going to be graphing them. We're going to be talking about the vertex, filling in tables, talking about what that means as far as the transformation from the parent function. I have another video about absolute value functions that focuses solely on using the TI-84 plus CE graphing calculator. So if you need some help with that, definitely take a look at that video. So we have a lot to discuss here. This is an introductory lesson into graphing nonlinear equations before I talk to my students about graphing quadratics, parabolas. I feel like if I can get everyone to understand exactly what it means to graph an absolute value function, then the quadratics are going to be very, very simple because they're going to follow in that same pattern and routine for the most part. Okay, so here we have the format for an absolute value function. It's f of x. We know f of x is really just another way to represent y equals when we're talking about a function. A. This letter A is going to do a lot. This letter A represents a number, and if that number, the absolute value of that number is greater than 1, so it's not a number less than 1, it's not a fraction of 1/2, it's more like 2 or 3 or even -3. Any value that you could take the absolute value and make it greater than 1, that's going to cause our function to stretch or get, okay? It's going to make our function, our graph is going to look like a V. It's going to make it more narrow. So if I have a value of 2, it's going to make it look like this, a value of 3, a value of 4, and the greater the A value, the skinnier the graph is going to be. If that A value, the absolute value of it, is somewhere between 0 and 1, so a positive 1/2, a negative 1/2, a positive 2/3, a negative 2/3, it's going to make the graph wider. So an absolute value function is going to look like a V-shaped graph. And if I have a fractional value A between 0 and 1, or negative 0 and negative 1 rather, it's going to make the graph wider like this. Last thing I need to let you know is that if that A value is negative, what it's going to do is it's going to reflect over the x-axis. It's a vertical reflection. So instead of the graph looking like this, it's actually going to look like this. So A is pretty powerful. It's going to control the shape of the graph, and it's going to control whether it's facing upwards or downwards. Okay. HK. So here I have A times the absolute. Okay, and then outside of the absolute value bars are plus K. This HK is so important. It's as important as the A value. The A value controls the shape and the direction. HK controls where the vertex of our graph is going to be. You see, if the absolute value function looks like a V-shaped graph, the point here where my two line segments meet, or my lines meet, is the vertex, that point. And the coordinates of HK are that vertex. Okay, HK is the vertex of the graph. I also typed in and added in here that it's also the shift of the parent function. So if I have my parent function right at the origin, which we're going to take a look at next, the vertex of my new graph, wherever that may be, actually is the shift. So it might be that I'm taking my parent function and moving it 3 units, 4 units, okay? And that's going to be my new vertex. If I give you an example of an equation here, a function here, f of x equals 2 times x minus 3, close the absolute value bars, plus 5. I'd be able to know, first of all, an A value of 2 is going to mean that my graph is going to be skinnier than the parent function. And then x minus h. So if I see x minus h, that means x minus 3. 3 is then the x coordinate of my vertex. Again, notice the format. It's x minus h. So if I see x minus 3, then that means that 3 is my h value of my vertex. Then whatever number is at the end here is my k. So it's positive 5, and that's my vertex, 3, 5. So I'm going to know from my parent graph, and again, we don't even know exactly what this is going to look like just yet, that it's going to be a skinnier version, and the vertex is going to be at 3, 5, and that's where that point of my V-shaped graph is going to be. So let's go ahead and actually graph the parent function. I'm going to guide you through a series of ways that I generally teach graphing. I feel like it's very straightforward, and we're going to follow that format for the rest. So the first thing I'd always want you to do is I'd want you to look at the parent function, notice it's just the absolute value of x, and figure out what the vertex is. So the vertex is hk. Do we see x being subtracted by any number? No. So that means actually h is 0. Do I see any number being added at the end of my function? K? No. So that means my k is 0. So the parent function, vertex, is actually at 0, 0. And I always encourage my students to put the vertex in the center of the table. Once you fill the vertex into the center of the table, you'll then fill in your x column with integer values that are 1 less and then 1 greater. So just a natural progression of x values increasing by 1s. So if my vertex is at 0, 0, I'm going to put that in the middle of my table. I'm then going to fill in my table 1 less and then 1 more. Now I can go ahead and actually just look back at my function and fill in my values. If I plug in a -2, what's the absolute value of -2? The absolute value of -2 is 2. The absolute value of -1 is 1. Let's go to the positive now. The absolute value of 1 is also 1. The absolute value of 2 is 2. So let's say I went ahead and I started plotting these points. -2, 2, -1, 1, 0, 0. I'm going to highlight that for my vertex. And now look what happens. 1, 1. We haven't seen this before. We're so used to linear equations that are a nice straight line. Okay, no bends to it, no curves. And now this absolute value function is going right back up. It's not wider than it should be. The a value, the number that's really here in front of my absolute value bars, is 1. 1 doesn't change the shape of anything, and it's good to go. Okay, this is the parent function. Every graph that we're about to do relates totally back to this function to begin with. And we're going to notice that going forward. All right, let's take a look at our next screen. Okay, we're going to be taking a look at, I'm just going to make my screen a little bit bigger here. We're going to be taking a look at different absolute value functions that we're going to be graphing. We're going to go through the process of looking at the function, determining the vertex. After we determine the vertex, we're going to plug that into the middle of the table. We're going to fill in our x column. We're then going to go ahead and fill in our y's, and we're going to graph it and see what's actually happening from that parent function. Okay, so y equals, doesn't matter if it's y equals or f of x equals, it's still our same function. Y equals the absolute value of x plus 1. So our format, if I went back to my other screen and I showed you and reminded you, it's a and then absolute value of x minus h and then plus k. So x minus my h value, and then my k value is my number at the end that's not within the absolute value bars. So here, if I have just the absolute value of x, that means that my h value of my vertex is 0. So I don't see x being subtracted by anything. My k value of my vertex is 1. It's what that number is at the end. That's going to be the vertex of my function. I'm going to put that vertex in the center of my table. Okay, the vertex goes in the center. I then fill in my x values, going 1 less and then 1 up. So -1, 2, and then below it would be +1, +2. Now I go ahead and I substitute each of these x values into my function to get my y value. So absolute value of -2 is 2. 2 plus 1 is 3. Let's plug in -1. Absolute value of -1 is 1, plus 1 is 2. Plug in +1 now. Absolute value of 1 is 1, plus 1 is 2. Absolute value of 2 is 2, plus 1 is 3. Now, do we see anything interesting about the y values? What do you notice? Hopefully you do notice that whatever my y value here was up top is the same as my bottom. And whatever was here is here. It's symmetric. And it should be, because think about it. If I have a V-shaped graph, I'm going to have my vertex in the middle. That's my 0, 1. And then my corresponding points are going to have the same y value. So my fingertips would have the same y value. They'd have a different x value, but they'd have the same y value. They're at the same height. Same thing if I look where my knuckles would be, okay? They have the same exact y value, but just different x values. And we actually had that in our previous problem as well. So let's go ahead and graph this. So -2, 3, -1, 2, 0, 1, and 1, 2, and 2, 3. So I'm going to go ahead here and I'm going to add in the graph of what the parent function actually looked like. Parent function was at 0, 0, 1, 1, 2, 2, -1, 1, -2, 2. What do you notice is the transformation from my parent function, the original graph, to the new graph? Its shape is the same. It didn't move left or right. It only literally moved up 1 unit. And so that's exactly what we want to be able to see. And that's actually what the vertex is telling us. It's not moving anything on the x-axis. It's not going left or right. It's only going a positive 1 unit up. My vertex actually gives me all of that information. Let's take a look at the next one. So y equals negative. So that's going to tell me my a value is negative. If I go back to my previous screens before, a negative a value is going to tell us that our graph is actually going to get reflected over the x-axis or reflected vertically. X minus 2, and then I don't have any number at my end here. So the format is x minus h. So if I have x minus h, that means my h value of my vertex is positive 2. It's always the trickiest part. It's x minus h. So if I see x minus 2, then my h value is that 2. I don't see any number at the end here for k, so my k value of my vertex is just 0. 2, 0 is going to go into the center of our table. We're going to then fill in our x values going by ones. So I'm going to subtract 1 going up. I'm going to add 1 going down. And now I'm going to go back and I'm going to fill in each x value into my equation to get my y value. So if I plug in a 0, 0 minus 2 is negative 2. The absolute value of negative 2 is positive 2. Now I have to multiply that by the negative in front. It's the very last step. So I'm going to backtrack for a moment. 0 minus 2 is negative 2. The absolute value of negative 2 is 2. Then make it negative. Let's plug in a 1. 1 minus 2 is negative 1. The absolute value of negative 1 is positive 1, multiplied by the negative in front. Now, some of you are immediately going to know what these two numbers should be because you saw the pattern here, so it's going to be very helpful. But let's just do the math. If I plug in a 3, 3 minus 2 is 1. Absolute value of 1 is 1. Make it negative, negative 1. Same as here. Not a coincidence. 4. If I plug in a 4, 4 minus 2 is 2. Absolute value of 2 is 2. Make it negative. Again, not a coincidence. If I plot these points, okay, 0, negative 2, 1, negative 1, 2, 0, 3, negative 1, and 4, negative 2. My graph looks like this. It's upside down because of the negative a value. It's got a vertex at 2, 0. So notice that's where that point is. I'm going to go ahead and I'm going to put the parent function back on our screen. So 0, 0, 1, 1, 2, 2. Negative 1, 1, negative 2, 2. So think about what's actually happening here. If I was to look at any point on this grid, what is happening is that the point is reflecting over the x-axis, okay? And it's also going 2 units to the right. So if I was to take my parent function, reflect my parent function over the x-axis, and I will do this for us in a different color so you can see what's happening. Imagine I reflected it over my x-axis. I did a vertical reflection, and then I moved it 2 units to the right. 1, 2. I'd be right there. And if I did that for every single point, it would perfectly map onto it, and that's exactly what's happening. So my parent function is reflecting over the x-axis, and then it's moving 2 units to the right. And that's exactly what this graph is telling me to do. Pretty good. Okay, we've got 2 more of this same exact skill. I hope you're right with me here for this. Okay, so y equals 2 times the absolute value of x minus 1. So my vertex should be x minus h. I don't see x being subtracted by anything, so my h value of my vertex is 0. My k is the number that's at the end, negative 1. That's my vertex, 0, negative 1. I'm going to go ahead and I'm going to plug in 0, negative 1 into the center of my table. I'm going to then fill in my x values, decreasing by 1 going up, adding 1 going down. And now I'm going to substitute each one of these x values into my function to get my y coordinate. So if I plug in a negative 2, ready? Absolute value of negative 2 is 2. 2 times 2 is 4. Minus 1 is 3. Let's try the next one. We plug in a negative 1. Absolute value of negative 1 is 1. Times 2 is 2. Minus 1 is 1. I already have my vertex in. Let's jump here. Again, we should know what these values are really going to be, but let's just do the math anyways, just to prove it. If I plug in a positive 1, absolute value of 1 is 1. Times 2 is 2. Minus 1 is back to 1. Last one, let's plug in a positive 2. Absolute value of 2 is 2. Times 2 is 4. Minus 1 is 3. Let's plot those points. Negative 2, 3. Negative 1, 1. 0, negative 1. 1, 1. And 2, 3. Now, I hope when you look at this graph, you're immediately going, hey, this doesn't even look like the same shape. Well, let's go back to the function. Which part of this function actually changes the shape of the figure? It's the 2. If the a value is 2, it's actually going to take our V-shaped graph and make it skinnier. Okay. Also, what I want you to notice is, notice this graph is not going up 1 to the right 1, up 1 to the right 1 like our other functions were. It's actually going up 2, right 1, up 2, right 1. That's where that 2 actually comes from. That's how skinny it's making it. If that 2 was a 3, then it would be going up 3, right 1, up 3, right 1, and it's going to be even skinnier then. My vertex at 0, negative 1, so not only is it getting skinnier, but the graph then got shifted down 1 unit. That's exactly what was happening. So it's being stretched vertically like this, so it's making it skinnier, and it's shifted down 1 unit. And if I draw the parent graph here back in red, we're going to see that same situation happen. I mean, look how much different the parent function looks. Yes, they actually share a couple of the same points, but my parent function, sorry for that bad drawing, my parent function is definitely wider. So this made it skinnier and shifted it down 1 unit. Okay, last problem. Y equals absolute value of x plus 2 plus 1. Okay, remember how I've said over and over that in the parent function, in the format, it's x minus h. I kept going over that, x minus h. So if it says x minus h, and then you have x minus 2, well, it just falls perfectly in line. It would be the h value of 2. Here, I see x plus 2. And I think some of you are already a couple steps ahead of me. You know what I'm about to show you. So look, it's x minus h. But I have my x value. I don't have a minus. My h is not actually 2. The only number you can plug in for h to actually make it become a positive 2 would be if it was x minus a negative 2. Think about that. If I have x minus a negative 2, x minus a negative 2 really becomes x plus 2. So that actually means my h value for my vertex is that negative 2 rather, I'm sorry, is that negative 2. My k value is always just the number at the end. The sign doesn't change. The sign gets to stay. So my k value, my vertex, is that positive 1. Negative 2, 1 gets put right in the center of my table. I subtract 1 going up, so negative 3, negative 4. I add 1 going down, negative 1, 0. And now I go ahead and I substitute each value in. Ready for the math with me? Negative 4 plus 2 is negative 2. Absolute value of negative 2 is 2. Plus 1 is 3. Let's plug in a negative 3. Negative 3 plus 2 is negative 1. Absolute value of negative 1 is 1. Plus 1 is 2. We already know what the bottom portion is going to be. If I plug in a negative 1 plus 2 is 1. 1 plus 1 is 2. Look how it perfectly matches. 0 plus 2 is 2. Absolute value of 2 is 2. Plus 1 is 3. I'm going to go ahead and graph these. So negative 4, 3. Negative 3, 2. Negative 2, 1. Negative 1, 2. 0, 3. I'm going to graph my parent function again, just so we can make the connections. So 0, 0, 1, 1, 2, 2, negative 1. Notice the shape stayed the same. It did not get skinnier or wider. That's because my a value here really in front is a little 1 that we don't see. It did shift 2 units to the left and then 1 unit up. And that's exactly what my vertex is. Negative 2, 1. It's telling me to shift this whole graph 2 units to the left and then 1 unit up. 2 units to the left, 1 unit up. 2 units to the left, 1 unit up. Awesome. I've got some really quick problems for us that I want us to be able to take a look at. Okay, the directions are the same for each. It says determine the vertex and the transformation from the parent function. So I'm going to go through these pretty quickly. Feel free to obviously pause as I'm going through this so that you can try some out and then press play and see how you did. So my first function here, f of x equals the absolute value of x plus 2. My vertex, my h is 0, my k is 2. This would tell me to just go 2 units up. 0 is my horizontal transformation. If I have a 2 for my k, it means the whole graph gets shifted up 2 units. F of x equals absolute value of x minus 3. H is 0, k is negative 3. That would tell me that my whole graph is going to go down 3 units. Next couple. F of x equals absolute value of x minus 1, and then minus 3. My h is 1. Remember, it's x minus h. So if you see x minus 1, my h value is 1, negative 3. So this is going to tell me that my graph is going to go 1 unit to the right, that's my horizontal, and then 3 units down. Okay, this is my x transformation, this is my y transformation. If it's positive, it's going to the right. If this was negative, it would have gone to the left. Next one, f of x equals the absolute value of x plus 2 plus 1. We went over this in one of the other problems. If it says x plus 2, then that h value is really a negative 2. The k is a nice positive 1. So again, it's x minus, I'm going to write on this again like I did before. Since it's x minus h is the formula, it would have to be x minus a negative 2 in order for it to actually become plus 2. So that h value is really a negative 2. Negative 2, 1 would give me a shift of 2 units to the left and then 1 unit up. Okay, vertex, my h is 0, my k is 0. So it's not moving anywhere, but an A value of positive 2 is going to make that graph get stretched out, much skinnier. All right, vertex, my H is 0, my K is 6. So that's going to tell me that it's going to shift up 6 units and then a negative A value. Do you remember what a negative A value does? It reflects it over the x-axis. So it's going to get reflected and then also shifted up 6 units. Last two. Vertex, x minus 3. So my H vertex is, part of my vertex is 3. My K is 0. So a half. If 2, a nice number greater than 1, makes it skinnier, a half, a value between 0 and 1, makes it wider. So this graph is going to get wider, and this H value of 3 is going to shift it 3 units to the right. Fancy word, vertical compression. Last one, x minus 4, so my H is 4 plus 1, 3. A value of 3 is going to make it skinnier, vertical stretch, and then it's going to go 4 units to the right. That's what this 4 means, and then 1 unit up. Thank you so much for joining me on this video. I hope it was very helpful for you. Take a look at my other videos if you need them.